In this video, I'm going to talk about logical functions, which include the operations AND, OR, and exclusive OR. I'm also going to talk about shifting and mention the compare operation. So let me talk about the AND, the OR, and the exclusive OR function. First, I want to describe AND. In this table, I'm showing two values, x and y, and what happens when you AND them together. So what are the possible values for x and y? Well, y could be 0 or 1, and x could be 0 or 1. And here are all the possible combinations of x and y. Notice these are just all the 2-bit binary numbers, 0, 1, 2, and 3. 0, 1, 0, 1, 0, 0, 1, 1. These are all of our combinations of x and y. Now, AND is defined to be 1 when both of the two arguments are 1. So if x is 1 and y is 1, then x and y, which is shown in this column, is 1. If either x or y is 0, then x and y is 0. So x and y is 1 in only one case. Now the logical function OR is similar, except it's defined to be 1 if either x or y is 1. If x and y are both 0, then x or y is 0. If either x is 1 or y is 1, or both are 1, then x or y is 1. And finally we have exclusive OR. Exclusive OR is defined to be 1 when its two arguments are different. So we can say that exclusive OR is the same as x does not equal y. When x and y are both 0, x exclusive ORed with y is 0. When they're both 1, x exclusive ORed with y is 0. But when they are different, the value is 1. Now, in this case, we were working on just 1 bit of x and 1 bit of y and getting a 1-bit result. In a computer, instructions generally work on more bits than just 1 bit at a time. So here's an instruction from the Intel architecture. You don't need to know too much about the Intel architecture, except that ECX and EAX are registers. One register is named ECX and the other is EAX. This is the assembly language instruction, and L means it operates on 32 bits at a time. So these are 32-bit registers, and so what this does is it takes the contents of ECX and EAX, and it ANDs them bitwise together, and it puts a result in EAX. So here we're seeing exactly what it does. Let's say the value of EAX is this, and the value of ECX is this. We AND them together. So it does it bitwise. 0 and 1 is 0. 1 and 0 is 0. 0 and 0 is 0. 1 and 1 is 1. And it keeps going like this through all 32 bits. And the result is this 32-bit pattern here, which is then stored in EAX. That is a 32-bit long AND instruction. And likewise, there are instructions for OR and exclusive OR that are 32 bits as well. Now let's take a look at the C programming language and see what this looks like in C. In C, we can have data that is char, or an int, or a short. Remember that char is 8 bits, int is 32 bits, and short is 16 bits. And we have operations. The ampersand is used for AND, the vertical bar for OR, and the caret symbol is used for exclusive OR. And so we might see statements like this in C. Let's assume that x, y, and z are declared to be shorts, okay, meaning that each has 16 bits. Well, here we're showing a 16-bit value for y and a 16-bit value for z, and we're ANDing them together. So everywhere that you have two 1 bits, you see a 1, but only where there are two 1 bits in the arguments do you see a 1. Everywhere else, there's a 0. So an operation like this will take a 16-bit operand y, a 16-bit operand z, treat them as bit strings, and perform the AND operation in a bitwise fashion to get a 16-bit result. If x, y, and z were declared to be integer, it would do 32 bits at a time. Or if char, it would be doing 8 bits at a time. The vertical bar is used for the OR operation, and here we can see that everywhere there's a 1, we have a 1 in the result. So lots of 1s. With AND, we tend to get lots of 0s. With OR, we end up with lots of 1s. With exclusive OR, it's mixed. So here's the exclusive OR operation. Everywhere they differ, we see a 1. Okay, everywhere the two values differ. They differ here, so there's a 1. They differ here, so there's a 1. But here and here, they're the same, so we have 0s. These logical operations are useful for manipulating bits in a word. So in order to turn on bits, the OR operation is used. So if you want to turn on certain bits in a word, then you use the OR operation. And we can refer to one word as the word that we want to modify, and the other as the mask word. So let's say we want to turn on x bits. Every other bit we want to turn on in this value. So here we have some random value. In hex it's 3A0F. And we want to take it and we want to turn on every other bit as well. So we want to turn on this bit. This bit's already on. This bit we want to turn on. This bit we want to turn on. This bit we want to turn on. And the others we want to leave the way they are. So we create a mask that has every other bit being turned on. In this case 0101, 0101, and so on. In hex it's 5555. And when we OR these things together, everywhere the original thing had a 1, we'll have 1s. So we have 1 here, and we have 1 here. But in addition, we also turn on this bit and this bit. Well, this bit's already on. And this bit, and this bit, and this bit, and this bit. So we use an OR to turn on bits. And we turn on the bit wherever the mask has a 1 bit. Now, if we want to turn off bits, we can use the AND operation. And in this case, we turn off bits in X wherever the mask has a 0 bit. So let's just take the same operation here, the same values, and let's say we want to turn off bits. So what we're trying to do is turn off this bit and this bit. So, and keep the other bits the same. So let's just keep the other bits the same. Where we have a 1, we keep them the same. So 1 and 1 is 1. 1 and 0 is 0. So we keep those bits the same. I'm going to write this a little bit bigger here. Everywhere we have a 1, we just copy the bits from up there. So we're going to copy this bit. Here we copy that bit. Here we copy that bit. We copy this bit and this bit. We copy this bit and we copy that bit. Now we go through and we turn off these bits because 0 and anything is going to be 0. 0 and 1 is 0. Here we turn off this bit and off that bit. Off this bit and off this bit. So we're turning off every other bit. Turning off this bit, this bit, this bit, this bit, this bit, and this bit. So we're using AND to turn off bits. And finally, if you want to toggle the bits, you use the exclusive OR function. So everywhere the mask has a 1, we flip the bits. So let's say we want to take this value here and flip all the bits. 0, 0, 1, 1, 1, 0, 1, 0, 0, 0, 0, 0, 1, 1, 1, 1. And we want to flip every single bit. So we just put all 1 bits there. Okay, and then we do the exclusive OR function. So 0 exclusive OR, well, they're different, so we have a 1 there. Here they're different, so we have a 1. Here they're the same, so we have zeros. Here they're the same. Here they're different. Here they're the same, and here they're different. Here they're different, and here they're the same. So now comparing our result to what we originally have, we see that we've just flipped all of the bits. So again, to turn on bits in a word, we use the OR instruction, and everywhere the mask contains a 1, we turn on the corresponding bit of our value. To turn off bits, we use the AND instruction, and everywhere the mask has a 0, we turn off the bit. The other bits we leave the same. And to flip, or to toggle the bits, change the zeros to a 1 and the 1s to a 0, we use the exclusive OR function. Everywhere the mask has a 1, we flip the bit. Now let's look at shifting. We can shift bits to the left, or we can shift them to the right. And first we'll talk about shifting left, and then we'll talk about shifting right. There's one operation to shift to the left, and there are 2 to shift to the right. So let's talk about shifting left first. Let's assume that we've got a 32-bit number. We've got a word value. We're going to shift these bits over to the left, and the bits that are most significant are going to get lost. They're just going to get shifted out into nowhere, and they're going to disappear. And we're going to shift a 0 in on the right-hand side. That's the way a shift left works. In C, we use the less than operator to indicate a shift left. In assembly language, well, in the Intel assembly language, we use the shift left instruction, SHL. The second L indicates that it's a 32-bit operation. Typically, we can have the number of bits to shift. So, for example, in this example, we're shifting by 5. And we specify a register containing the bits that we want to shift. So in this operation, we're shifting left by 5 bits. So if the value of the EAX register contains this bit pattern, then we move these bits over. So this bit goes to 1, 2, 3, 4, 5 to right here. And so we get this result, and zeros are shifted in. These zeros here are shifted out and lost. Now we should also note that shifting to the left is a fast way to multiply by 2 to the n. Okay, if n is, for example, 5, 2 to the n is 32. So if we want to multiply by 32, we can just shift left 5-bit positions. And let's look at these bit patterns and see how this works. This bit pattern corresponds to the number 3. If we shift it left 5 positions, we get a number that is, well, let's talk about our place values. 1, 2, 4, 8, 16, 32, and 64. So we have 64 plus 32, and that's 96. Well, if you multiply 32 times 3, you get 96. So in fact, yes, we have multiplied this thing by 32. Multiply in a computer is a very expensive operation. It's hard for us to do by hand as humans, and likewise it's hard for the computer to do, and in general it's time consuming. Shifting, on the other hand, is something that the computer can do very fast. So it's almost certain that this shift operation here is going to execute much faster than a multiply operation, maybe 10 times as fast. So this is a much better instruction to use rather than to do a multiply by 32. Now when we shift right, we're going to shift the bits in the other direction. The least significant bits are going to be lost, and we're going to shift something in on the left. And here's where the difference is. We can shift in a 0, or we can do sign extension. In other words, we just copy the sign bit. If it was a 1, then we shift in a 1. If it was a 0, then we shift in a 0. Shifting in a 0 on the left is called a logical shift. And shifting in the sign bit is called an arithmetic shift. So we can shift right logical or shift right arithmetic. On the Intel architecture, we have an SHR, shift right, for the logical, and SAR for shift arithmetic right. And so these are two examples of the instruction. And here's an example showing that we're shifting to the right by 3. And just as shifting to the left is a fast way to multiply by 2 to some power, shifting to the right is a fast way to divide by 2 to some power. So for example, shifting right 3 bits is equivalent to dividing by 2 to the third, or dividing by 8. And we lose bits off the least significant end, and so we effectively round, and we round down toward negative infinity. So that is the shift operation. There's one left shift, and in C it's the less than, and there are 2 shift rights. And the C specification in the C language says it's implementation dependent on whether this operation does a logical shift or an arithmetic shift. So be aware that these are dangerous operations to use if the number is a signed number, or I should say if the most significant bit is a 1. Although this is getting a little bit away from the topic of data representation, I also want to mention at this time the compare instruction. So from time to time we want to compare 2 numbers to see which is less than or greater than. And there's an instruction called compare, CMP. And here's an example from the Intel 32-bit architecture. L means we're going to do a 32-bit compare. We're going to compare 2 32-bit numbers. And the way we can compare numbers, let's assume that the 2 numbers are in registers. One number might be an immediate number. And in this example, actually, I have an immediate number of 73, and the other number's in a register. But in some cases, both numbers may be in the register. You execute the compare instruction, and you follow that generally with a jump instruction that's a conditional jump instruction. The way this works is the compare operation sets some condition code bits in the processor. There are 3 or 4 bits that are set after arithmetic operations, and the compare operation is considered to be an arithmetic operation. Nothing has changed, the registers are not changed, nothing has changed except the condition code bits. So these things are sometimes called condition codes, or the integer condition codes, or the status register. In any case, there are several bits, usually about 4 bits, in each architecture, and they're set according to whether the numbers are equal or whether one's less than the other in an unsigned comparison, or whether one's less than the other in a signed comparison. So the next instruction would normally be a conditional branch. So in the Intel architecture, to compare the value in register EAX to the number 73, we would do it this way. And then in this case we're jumping if the comparison results in less than or equal. So we're jumping to a label loop if the value in EAX is less than or equal to 73. Now notice that we're saying less than or equal x less than or equal to 73, not 73 less than or equal to x. The order here is reversed for the Intel architecture. So we have 73 here and our x here stored in register EAX. And we're comparing, and we're jumping if less than or equal. So what we're saying is if the value in this register is less than or equal to this value here, so they're reversed, it's I think the most helpful way to write this assembly code is to put a comment here to put these things in the reverse order, okay, but have the sense of this be exactly the same as this and the jump to the loop. So what these two instructions do together is they say if the value in the register is less than or equal to 73, then we jump.